So this is the time independence Schrodinger equation we have. Okay, so our first step is, what I will do is I will introduce a new variable theta, and this is defined as square root of m omega by h cross into x. So why did we introduce a new variable? Okay, if you look at the dimension of this new variable theta, you can find that the theta is dimensionless. And why we are going for a dimensionless quantity, we will get the answer later while solving this differential equation. Okay, so for the time being, let's keep this in mind. The theta is a dimensionless quantity, and the reason we will find later. So theta is a dimensionless quantity. Okay. So then, if theta is dimensionless, un by dx, I can write dun by d theta into d theta by dx. Now d theta by dx is nothing but square root of m omega by h cross. So this will become dun by d theta square root of m omega by h cross. And if you differentiate again, d square un by dx square. So I have to differentiate this with respect to x. Then first differentiate with theta, then find d theta by dx. So this will become d square un by d theta square into d theta by dx, and currently square root of m omega by h cross. It's just a constant. And d theta by dx again is root m omega by h cross. So this will be equal to m omega by h cross into d square un by d theta square. Okay. So then I can substitute this complete a change of variable in this differential equation. Okay, so I can replace my un of x with un of theta, and d square un by dx square I can write as m omega h square d square un by d theta square, and x square I can write h cross by m omega into theta. So this equation will become minus h bar square by 2m m omega by h cross d square un by d theta square plus half m omega square, and instead of x square I can write h cross by m omega theta square un of theta, and that will be equal to en into un of theta. So here one h cross would cancel, one m would cancel, and I will get minus h cross omega by 2 d square un by d theta square. Again h cross m would cancel omega, so plus h cross omega by 2 theta square. So I can take my this en to the left side, so it will become minus en un of theta equals 0. So throughout I can multiply by minus 2 by h cross omega. So multiply throughout with minus 2 by h cross omega. So there will be only d square un by d theta square here, plus, so minus become 2 plus 2 en by h cross omega become minus theta square un of theta equal to 0. Now this quantity 2 en by h cross omega I am going to denote by with another symbol epsilon n, and my differential equation will take the form d square un by d theta square plus epsilon n minus theta square and u n of theta equals 0, where epsilon n equal to E n by x cross omega. Okay, so this is my differential equation in terms of the new variable theta. Now, how to solve this problem? So, the first thing is, I will use an assumption. I will go for an asymptotic solution. That is, what would be solution when theta is very large, when theta tends to plus or minus infinity. Okay, so that is called asymptotic solution. So the asymptotic solution is when what would be un of theta when theta tends to plus or minus infinity. So when theta is very large, it will be very large compared to epsilon n. Then this term epsilon n can be neglected, and I can rewrite my differential equation as d square un by d theta square minus theta square un of theta equal to 0. So its solution is very straightforward. That is, if you differentiate un 2 times, you have to get theta square and un constant. So this is possible when un of theta is exponential function of theta square by 2. So the possible form of un of theta would be some constant capital A into e raised to minus theta square by 2 plus some constant b raised to theta square. So there are two possible solutions for un of theta. It is either e raised to theta square by 2 or e raised to minus theta square by 2. You can check yourself. If you differentiate e raised to theta square by 2 times, you get theta square times e raised to theta square by 2. Okay. So therefore, un of theta in general would be the superposition of both the function, and this is valid when theta tends to plus or minus infinity. When theta is very large, this is valid. Okay. But among this solution, one of the term will not satisfy the normalization condition of the wave function, because we know that the wave function must be normal. That is, if you integrate the mod square of the wave function over the entire space, you should get 1. So therefore, the wave function must vanish when you are going away from the origin. Okay, so if that is the case, then un of theta must tend to 0 when theta is very large. But among these two solutions, one of the solutions is divergent. That would increase the theta. If you look at e raised to theta square by 2, e raised to theta square by 2 increases when theta increases. Okay, so then we cannot normalize this un of theta. So in order to satisfy the normalization condition, the wave function must converge, not diverge. So in order to obey that, I have to neglect this term. So therefore, I have to set beta 0. So this b 0. So b must be 0, since un of theta must be convergent. So b must be 0. Okay, so why we are setting b 0? Because otherwise un of theta would be a divergent function. We cannot normalize it because it will increase un of theta. Otherwise un of theta will tend to infinity when theta tends to infinity. So since b is 0, I can write my un of theta as some constant in the e raised to minus theta square by 2. So beta is 0. The reason is the wave function must be convergent or normalized. Okay, so in order to satisfy this condition, the only possibility is un of theta must be exponentially e raised to minus theta square by 2. Okay, so this is a form of un of theta when theta is very large. But in general, what would be un of theta? Then the possibility is un of theta must be product of two functions. So one of the function must be e raised to minus theta square by 2. So we can have an assumption. It is called ansatz. So a general form of un of theta A general form of un of theta for any theta value, un of theta I can write some function f of theta b raised to minus theta square. Okay, for large theta, the un of theta will take this form. Otherwise, you have and the term f of theta as well. Okay. So next, what is this f of theta? F of theta, the differential equation for f of theta can be found by yourself, and there is another assignment to you. Okay, so the step is you can substitute this un of theta into this differential equation, and some of the term would cancel, and we can simplify it, and while simplifying you will get the differential equation for f of theta is of the form d square f by d theta square minus 2 theta df by d theta plus epsilon n minus 1 f of theta equal to 0. So this will be the equation that you will get, and you have to do this step as homework, and you have to post your answer as your assignment. Okay. So that is leaving to you this simple step that you can do it yourself. Okay. Now this is a differential equation now you got. Now how to solve this? This is the next question. Now there is a beautiful way to solve a general differential equation using a series solution method, or it's also called the Frobenius method. Frobenius. That is, you can expand your f of theta as sum over m am theta raised to. Okay. So any function you can f of theta can expand in terms of the powers of theta. So theta raised to 1, theta raised to 2, theta raised to 3 plus etc. And there will be some expansion coefficient also, a0, a1, a2. So it's m running from 0 to infinity. Okay, so for m equal to 0, theta raised to m, theta raised to 0 would be a constant term, then a theta dependent term, theta square dependent term, so on. Okay, now you can tell why we introduce a dimensions quantity theta. You got the answer? Because in order to expand a function in a series method, the function variable of the function must be dimensionless. Okay, so earlier we have a dimension quantity x, and you have un of x. You cannot expand un of x in this particular form because x has a dimension. What is the problem with the dimension? So if the x has a dimension, then you will get many quantities, many terms while expanding this summation. First term would be a constant term, second term would be x dependent term, the third term would be x squared term, so on. So that means the first term would be dimensionless, the second term has a dimension of length, and the third term has a dimension of area, and so on. And that is unphysical. You cannot add the quantities of different dimensions. Okay, so in order to represent a function in a series form, the variable of the function must be dimensionless. So that is the relevance of theta. So that is why we introduce a new variable theta. Okay, it is not for just changing the variable. It is purposefully we have changed into a dimensions quantity, and the reason is this, because in between we will experience such kind of series solution method. So we can use this method if your variable is dimensionless. Okay. Now I can find the conditions on AM. If you know the condition of AM, I got the solution. Okay, so what are the conditions for AM? So for that, just substitute the f of theta form in this particular differential equation. So we have f of theta and df by d theta and d square f by d theta square. So what would be df by d theta? So df by d theta would be sum over m equal to 0 to infinity am m theta raised to m minus 1, and d square f by d theta square would be sum over m equal to 0 to infinity am m into m minus 1 theta raised to m minus 2. Okay, so better I will remove this part. Okay, so now just substitute all these things into our differential equation. So d square by d theta square is simply sum over m equal to 0 to infinity a m into m minus 1 theta raised to m minus 2 minus 2 theta times df by d theta. So df by d theta is sum over m equal to 0 to infinity am to m and theta times df by d theta. So theta times theta raised to m minus 1 would give theta raised to m and plus last term epsilon n minus 1 sum over m equal to 0 to infinity am theta raised to m equal to 0. Now this equation must be valid for each and every power of theta. It should be valid for theta raised to 0 independently, theta raised to 1 independently and so on. So it should be valid for each powers of theta independent to each other. So for a particular power, consider theta raised to L. So for theta raised to L, this first term would be, so you have to make theta raised to L, this m must be L plus 2. So it should be AL plus 2. This A term should be AL plus 2 and here theta raised to m, theta raised to m, so we can have a simple calculation. So for theta raised to L, this equation term will be AL plus 2 into L plus 2 into L plus 1 theta raised to L minus and it should be AL to L theta raised to L plus epsilon n minus 1 into AL theta raised to L equal to 0. You can take theta raised to L to the right side. So that for this equation must be 0 independently and I will get a recurrent relation. So AL plus 2 I can write this will be to the right side, will become epsilon n minus 1 epsilon n minus 1 epsilon plus 2n minus 1 divided by n plus 2 n plus 1 into a. So such equation is called recurrent relation. So recurrent relation for the expansion coefficient am. Okay, so this L, okay, so this L is just a dummy index, so you can replace this L with m. I can write am plus 2 is epsilon n plus 2m minus 1 divided by m plus 2 and m plus 1. Okay. Okay, now here if m is very large, for large m, this am plus 2 will take the form, it will be 2m by m square, so it will be approximately 1 by m by 2. Okay. Then am will become am will become 1 by m minus 2 by 2 m minus 2. So therefore am plus 2 I can write 1 by m by 2. Then am would be 1 by m minus 2 by 2 etc. to a0. Okay. So what is this? So then what I can do is I can write my am is approximately, or am plus 2 is approximately 1 by m by 2, 1 by m minus 1, or m by 2 minus 1, 1 by m by 2 minus 2, etc. up to a0. So approximately if m is large, whether am plus 2 or am is almost same, so they will get the functional form of am. So the functional form of am is approximately will take the form 1 by m by 2 factorial is 1 by m by 2. Okay, so if am is approximately taking this form, I will get the approximate solution for f of theta. So what will be f of theta? F of theta is sum over m a0 theta raised to m divided by m by 2 factorial. So I can put my m by 2 as L. If I put m by 2 equal L, so m I can write as 2L. So this becomes sum over L a0 theta square raised to L divided by L factorial. So a0 is just a constant, I can take this a0 outside. So theta square by L factorial and summing over L is nothing but e raised to theta square. Okay. So f of theta will take the form a0 e raised to theta square. Is this equation or is this solution valid? Okay, you can go back to your un of theta. Un of theta is f of theta e raised to minus theta square by 2. If you put f of theta as e raised to theta square, then what will happen? Un of theta will become e raised to plus theta square by 2. That will not obey the normalization condition, the convergence condition. Because if un of theta is e raised to theta square by 2, that will diverge when theta tends to plus or minus infinity. Okay, so we can discuss it on the left side. Okay, so if f of theta is sum over L equal to 0 to infinity e raised to theta square raised to L by L factorial, and as it is outside, will become a0 e raised to theta square. And if f of theta is a0 theta square, then un of theta will take the form e raised to theta square by 2. It will not obey normalization condition. Okay, so that means you cannot write f of theta of this particular form. Okay, so then what is the another way for it? So we know that f of theta must be a single solution. Okay, and I got the explicit form of m as well. But if this m running from 0 to infinity, then the issue is f of theta take the exponential form, and this un of theta, the eigenfunction, the energy eigenfunction will become divergent. So then there is only one way to solve this issue, the divergence issue, what you can do is, you can truncate the series of f of theta. So don't let f of theta, the summation, run from 0 to infinity, just truncate it somewhere. So if you truncate f of theta at some position, some point, at some indices, then f of theta cannot be written as an exponential function. It will be just a series. It is a series of finite number of terms. If f of theta is the sum of finite number of terms, it cannot become exponential. Then this problem is solved. So in order to do away the divergence issue, what you can do is, you can truncate the f of theta. So solution to solve the divergence issue is to truncate series of f of theta at some m. Okay, so here the series is running from m equals 0, 1, 2, 3, 4. At some m, we'll truncate it, we'll stop it. Okay, so where to stop, that we don't know. Okay, so we can have a different possibility. You can stop at m equals 0 itself, then you will have only one term, this is only constant term. We can stop at m equal to 1, we can stop at m equal to 2, m equal to 3, etc. Okay, now you have to remember one more thing. So anyhow we have to stop f of theta, and we have many the coefficient a1, a2, a0, a1, a2, a3, etc. But there are some restrictions for a0, a1, a2. The thing is, if you look at the potential energy of this particular problem, V of x is an even function. Since V of x is an even function, the energy eigenfunction must be either odd function or even function. Okay, it should be either odd or even. So that is the condition. So we have a small result. That is, if V of x is an even function, then the wave function must be either odd or even. So therefore, if you look at f of theta or un of theta, un of theta is a product of f of theta e raised to minus theta square by 2. Now e raised to minus theta square by 2 is always an even function. So therefore, your f of theta can take either odd form or even form. Okay, it should be either odd or even. So either odd or even means f of theta. So if f of theta has odd powers of theta, then all even powers of theta must vanish. So if f of theta is an odd function, then it should have only odd powers of theta. It should have either theta raised to 1, theta raised to 3, theta raised to 5, etc. Then it cannot have theta raised to 0, theta raised to 2, theta raised to 4 term. And similarly, if f of theta is an even function, then it cannot have odd powers. So this implies that f of theta must be either odd or even. Okay, so if it is an odd function, say if f of theta odd, then your a0, a2, a4, etc. must be 0. And if f of theta is an even function, then the term like a1, a3, a5, etc. must be 0. So this is an additional condition for f of theta. So we already decided to truncate the series of f of theta, and another condition is from the even nature of the potential we have found that it cannot have both odd nature and even nature. It can have either odd function or odd term or even term. Okay, so then we can check what are the possible wave functions for this particular problem. Of theta, and I found that the f of theta cannot go to the summation of some series of f of theta cannot go to infinity. It should truncate at some point. Okay, so f of theta must be truncated. So let us suppose f of theta is truncated at kn plus 2. Let's put n plus 2 is 0. If n plus 2 is 0, then all other higher terms will be 0 because am plus 2 and am are interconnected. Okay, so if you remember, am plus 2 is 2m plus 1 minus epsilon n divided by m plus 1 m plus 2. Okay. So this is the recurrent relation. So I think I have made a small mistake earlier. It is while writing am plus 2, I think I have put minus 1 and plus epsilon n earlier. Okay, so you might have noticed it at that time itself. So this is the correct expression. So if you also made a mistake, so please correct it, go back and correct the recurrent relation. Okay, so the rest of the discussion did not differ any other discussions, so all the justification everything are same, but unfortunately I have made that mistake earlier. Okay, so please correct it, please do the step carefully. So it should be a minus epsilon n plus 1. Okay, so if you triangulate the series at n plus 2, the n plus 2 must be 0. N plus 2 0 means the possibilities an cannot be 0, then the numerator must be 0. Okay, so the numerator must be 0. So an plus 2, if you set 0, then that will imply 2n plus 1 minus epsilon n must be 0. Or epsilon n must be equal to 2n plus 1. And we have already defined what is my epsilon n. And epsilon n is nothing but 2 en by h cross omega, which is 2n plus 1. And therefore En I will get n plus half h cross omega. So if you triangulate the series at an plus 2, you will get the corresponding the energy eigenvalue as En, which is n plus half h cross omega, and the corresponding wave function I will denote by symbol En, because un is the energy eigenfunction corresponding to En. Okay, so I have got the possible energy eigenvalue just truncating the series. So this is very remarkable. That is by just from a simple mathematical step which we have introduced to solve the divergence problem, we have ended up in quantization of energy. So if you look at this expression, this n is an integer. N cannot take any value, n is an integer. Therefore, the possible energy eigenvalue become discrete. And what is the lowest value for n? The lowest value for n, that is the lowest value for an plus 2, that is a2 can be 0. That is the lowest possible truncation. a2 can be 0. So if a2 can be 0, that is the lowest possible value for n is 0. That is the lowest possible value for energy would be half h cross omega. So that means a harmonic oscillator in quantum mechanics, a harmonic oscillator always have a lowest possible energy, and which is half h cross omega. It cannot go below that. Okay, you cannot increase the energy of oscillator for lesser than half h cross omega, and this half h cross omega is called 0 point energy. And moreover, the energy become quantized. So this is very the beauty of quantum mechanics. Okay, so just from this step, just truncating the series in order to make the solution physically possible or physically explainable, we have ending up with the quantization of energy eigenvalue. So that is the remarkable result. Okay, so it's not only quantized, and we are getting one more thing. There is a lowest possible energy, and the lowest possible energy cannot be 0 for harmonic oscillator. There is always a 0 point energy, and that would be equal to half h cos omega. Okay, and the difference between each consecutive energy level, if you look at this expression, each consecutive energy level would differ by h cos omega. Okay, so the entire details we are getting from here. Okay, so the next is we will check up what are the wave function form and the energy eigenvalue form for lower derivation, that is for n plus 2 0, a20, a10, etc. For lower derivation, for the lower state, lower energy state, what are the possible wave functions and its the wave function graph we can